Okay, 5.2, power and polynomial function. So this section is going to be a little bit weird on its own. It's fairly definition heavy, but we are going to be building into, ideally, being capable of drawing kind of complex graphs. So we will have to certainly know these definitions, and it will give us a starting point once we get into that section. So rough definition, a power function is anything that can be written as kx to the p, where kp are real numbers, p we call that the power, k we call it the leading coefficient, and we call x the base. But k is very important. We talk about leading coefficients a lot in this section and throughout the next couple of ones. So what's kind of interesting about power functions is it's not really different every time we draw a graph. What that means is that if I have anything that's an even power, I have this picture of this graph right here. These are three different graphs. One of them is red, one of them is blue, one of them is green. Do I label them? No, I don't. One of them is x squared, one of them is x to the fourth, one of them is x to the sixth. So they do look a little bit different, obviously. But something that's worth noting is that they all seem to be doing the same thing when we go all the way to the left of the graph and all the way to the right of the graph. And we can see that again with odd powers. The first odd power that we have is in this graph, just y is equal to x, which looks very different from the other graphs. And then I believe one of them is x cubed, one of them is x to the fifth. And aside from the fact that, yeah, they do look different, especially kind of close to the origin, is that the end, they are going in the same direction. So as I go to the right side of my graph, all of those graphs go up. And as I look towards the left side of my graph, all of those go down. And so that's kind of cool that these follow a pattern. Anything that has an even power will either go all up or all down, and anything that has an odd power will kind of flip sides. So we kind of gather that information in this table. And these are the only four cases that we'll see. We'll have even powers where your leading coefficient k is positive, where it's negative, and then we'll have odd powers where it's positive or negative. So in the previous slide, we saw the positive cases. So if an even power is, we have a leading coefficient with an even power that is positive, then we have kind of the classic parabola or graph that looks like that. And so if we talk about end behavior, it's kind of maybe a little overwhelming looking at this table at once. So let's just look at the very top left box that has that x squared graph in it. When we talk about end behavior, we say as x goes to infinity, which means as I go to the right side of my graph. That's a really fancy way of saying as I go to the right side of my graph. So when we look at this, as I move to the right side of my graph, well, my graph goes all the way up, which is, it's going to go forever, all the way up to positive infinity. Now, if I look towards the left side of my graph, the same thing happens. My graph goes up, 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 so it goes all the way to positive infinity. And so that's how we talk about end behavior. And if you go into calculus later, you will see this notation a lot. Is yes, we're talking about as x goes to infinity, what's happening to your graph? Well, as we go to the right side of the graph, what's happening? And as x is going to negative infinity, as x is going to the left side of your graph, what is your graph doing? Is it going up? Is it going down? Is it staying at the same value? So to see that again, I think we go stick in the even powers we do. And so we can see this again on the bottom left graph now. We're saying, okay, what if I have a graph with an even power with a negative leading coefficient? Well, it's the exact same graph that we saw top left, except for flipped. It's a negative in front. So everything is going down versus going up in this case. So again, as the phrasing goes, as x goes to infinity, f of x goes to, well, in this case, negative infinity, goes all the way down. And as x goes to negative infinity, f of x goes to negative infinity again. Both of them are going down. Moving on to the odd powers. Odd power, as x goes to infinity, we can see that in this graph, goes to positive infinity. As x goes to negative infinity, f of x goes to negative infinity. And then if we flip the sign, if we make k negative, that flips our graph and we see that as x goes to positive infinity, f of x goes to negative infinity. As x goes to negative infinity, f of x goes to positive infinity. Now this is, again, a little bit weird and a little bit overwhelming with notation, but this is kind of what we're asking when we are writing an answer to n behavior. Yes, it's important to know the concept, and yes, when we get into graphing, the concept is much more important than this notation, but this notation is common. So if I were asked a question that was like, what is the n behavior of this graph, I would always be saying as x goes to infinity, and then I would describe what's happening in my graph. And I would say as x goes to negative infinity, I would describe what's happening with our graph. So it is that kind of what filling in the blanks did when we went through this slide. Now, to kind of see this in practice, I kind of shrunk down the table so I have a little bit of space to look over a question. This question says, describe the end behavior of 2x to the 6. Now, it doesn't really matter exactly what the graph looks like. That's not what the question's asking for. If you have a graphing calculator, great, but I wouldn't even want you to sketch a graph. Instead, I would want you to identify things on your table. Okay, well, 2x to the 6, that's an even power. My k is positive, it's positive 2. And so I can look at my chart and see, okay, as x goes to positive infinity, my graph goes to, well, oh, I guess I went with negative. As x goes to negative infinity, my graph goes to positive infinity. And as x goes to positive infinity, my graph also goes to positive infinity. So this is kind of how we're going to start seeing this applied, is we're going to actually look at a function and then relate it back to where that falls into our chart. See this again. Now we have negative x to the 7th, and it looks like I don't have the leading coefficient, but in this case there is kind of that invisible 1 in front of my x to the 7th. So I have an odd power. I have a negative leading coefficient. It's negative 1. And so I look at my chart, and the chart is the bottom right thing. So now my answer would be as x goes to, what do I start with? As x goes to negative infinity, f of x goes to positive infinity. And as x goes to positive infinity, f of x goes to negative infinity. And you could start either direction. You could say, typically kind of the standard is that we talk about the left side of the graph, then the right side of the graph. You could go right side of the graph, left side of the graph, or as x goes to negative infinity, describe your graph, and as x goes to positive infinity, describe your graph, or you could flip it as x goes to negative infinity like we have written here. Really, the important thing is you're saying what's happening on the left side of the graph. I'm going to describe f of x there. What's happening on the right side of my graph? I'm going to describe my f of x there. Whew, that's a little bit long-winded. Okay, moving on. Polynomial functions. So this is a very general form, but we see polynomials again and again and again. I still see polynomials in kind of my graduate courses because it is kind of the standard or the general form of the way that we look at numbers. A lot of things, a lot of functions fall into this category. And so some notation to talk about is when I have this polynomial function of this kind of weird form of variables flying around and anything like that, the biggest power, my nth power, is we call that my degree. We call my leading coefficient is that k. And then the red thing should say leading term, not leading coefficient. But really the important thing is degree, and then we already saw this before that the leading coefficient is k. And the reason why those things are important is we're going to tie this back to the polynomial functions. But for starters, before we get ahead of ourselves, let's just talk about identifying these terms. So I want to see what my leading coefficient is and my degree. So looking at this question, okay, the highest power, I have a constant term, I have x to the first, I have x to the 6. So my degree is 6. And then my leading coefficient is always what's next to that highest power. So I don't really care what's happening with my other terms. My leading coefficient is going to be negative 2. It's what's next to my x to the 6. Now, if you are going through a textbook that's very careful about how they're doing it, or you're reading over someone's work that's really good at simplifying things, they generally will write things in the form of highest power, then the next highest power, then the next highest power. Like that is kind of the standard way to write things. That doesn't mean that's always going to come out that way, especially if maybe you're doing some of your own work and you didn't rearrange it because you don't have to. Like you can write, if you were to simplify something in question B, that's a perfectly fine form. I'm not going to dock you if you don't have x to the third first. So all that's to say is we have to be a little bit careful. We don't just look at the very first number or the very first term. We look through all of the terms and say, okay, what's my highest power? So in this case, even though it's not the first thing that I see, my highest power is x to the 3, or specifically my highest degree is 3. And then the leading coefficient, the thing that is tied to that highest power, that x to the third term, is -6. I may have said it before, and I'm saying the definition a lot on this slide. A term is just a number and a variable by itself. So a has 3 terms, -2x to the 6 is one term, 5x is another term, and 1 is the third term. So I don't want to kind of keep using a word if I don't ever really define it. Now, the whole purpose that we're kind of went through those power functions is power functions are very specialized. You don't see a whole lot of expressions or equations or something that just has a single term, just has a single -2x to the 6, and that's it. It can happen, but it doesn't always happen. Well, the nice thing about this is that all of those rules that we came up with, that giant table with that end behavior, everything like that, can be used when we're doing the polynomial functions. And how we use them is we actually look at these two concepts, my degree and my leading coefficient, because those are kind of the strongest things, that's a very loose term, the strongest things in my function. So that's really going to drive what my end behavior is going to be. So again, I'm pulling down part A of example 1. I want to identify the end behavior. Well, I'm going to do that by looking at what my degree is and looking at the sign of my leading coefficient. Well, we saw my degree is 6. We saw my leading coefficient is -2. So we have a negative even function. So looking at this chart, pulled it over. Okay, bottom right, I have my end behavior for when k is less than 0 and it's an even power. So my end behavior will be as x goes to positive infinity, f of x goes to negative infinity, and as x goes to negative infinity, f of x also goes to negative infinity. Now, this part's a little bit of a review, finding intercepts. We've seen finding intercepts several times, but it is very important. It's worth repeating, so let's see it one more time. Well, I'll see it a couple more times in the semester, but let's see it an additional time right now. Okay, so finding my intercepts, it's always kind of, I plug in 0 for one of my variables and I solve for the other. So in this case, I'm going to start by finding my y-intercept. I plug in 0 for all of my x's, and I see that, okay, well, 0 minus 1 is -1, 0 plus 1 is 1, 0 plus 3 is 3. I multiply everything through. My y-intercept is 0, -3. Make sure if you're doing intercepts, you have to write them as points. Now, to find my x-intercepts, I flip the process. I set my f of x equal to 0 and my y equal to 0, and I solve for x. Well, the nice thing about this is I don't even have to factor. It's already in factored form. So I can set each part equal to 0 and then solve, and it's just a one-step solving process, but I would say x minus 1 is equal to 0, so x is equal to 1. X plus 1 is equal to 0, so -1, 0 is an intercept. X plus 3 is equal to 0, so -3, 0 is an intercept. If it gets a little bit more complicated, if you have some more things flying around in your each individual factor, you should kind of write out the steps. I kind of just did a little shortcut. Okay, well, to determine my end behavior. Now, this is kind of a bit of a shortcut. So the long cut, and if you don't feel comfortable with this shortcut, definitely take this route every time. It's just more work. Is that if you have something in this form, if you have something already factored, well, what I can do is I can look at how many terms I have and if there's any powers associated with it. I'll term each factor. So the first factor, x minus 1, has a power of 1, there's that invisible 1. X plus 1 is a power of 1. X plus 3 is a power of 1. So if I multiply all of these things together, I know that I would have something of a power x to the third. And that is kind of how you should do it. You should multiply everything out. You should FOIL it. You have to FOIL once, and then you have to multiply a binomial by a trinomial, and it's certainly doable. But if you think about it for a little bit and say, okay, well, if there's 3 powers, I'm going to multiply it out, you know that you're going to have a power x to the third, and that's going to be your highest power. And maybe, I mean, in this case, it's not really that hard to see what k is, but maybe we have some numbers in front of our x's. That's perfectly fine. Really, we're concerned about the sign. So my shortcut is, okay, I see I have 3 different factors. I multiply them together, I'll get x cubed. And what's in front of them? Okay, well, there's a 1 in front of my first x, there's a 1 in front of my second x, there's a 1 in front of my third x. Well, if I multiply it through, I will have 1x to the third. I recommend multiplying it out, checking it, making sure that I'm not just making up stuff, but that will be your biggest term. And yes, there will be a lot of other terms down the line, and yes, they'll probably have maybe weird numbers. They won't all have 1s in front of them. That's definitely true, but we know that doesn't affect our end behavior. The only thing that matters when we're talking about end behavior is our largest power, our degree, and our leading coefficient. So quite often, if it is in factored form, you can kind of logic your way through it and maybe write a little bit of work justifying your logic. If you don't want to do that, if you get stressed out like I do when you're taking tests, just go ahead and multiply it out. You will get the same result, and that is actually a much safer way to do it. Okay, again, that was long-winded, but in this case, 3 factors, multiply them together, I'd get a degree of 3, and I would get a leading coefficient of 1, which is positive. So now I'm going to look back at my chart. I pulled a piece of it. This chart, when I have a positive k and a degree of 3, that's an odd power. So my end behavior will be as x goes to positive infinity, f of x goes to negative infinity, and as x goes to negative infinity, f of x goes to positive infinity. Okay, turning points. Turning points, I don't want to kind of belittle them. Once we get into the very involved process, it's kind of built into if you've done everything right, you're going to get the correct amount of turning points. All of that being said, I'm pretty sure there's a WebWorks problem, and there might be one question on the test kind of relating these cute little properties, so it is worth mentioning. So a turning point on a graph is kind of exactly what you would see or what you think it would be. If you start to draw and let's say you're going up and then while you're moving down, that's a turning point. You're going down and then you have to move up, that's a turning point. And so a kind of cute relationship between degrees and turning points is that your minimum degree is always equal to your number of turning points plus 1. And we can kind of flip this idea. Your maximum number of turning points has to be equal to your degree of minus 1. So to see that in practice, this, if I'm just giving you a function, f of x, f times x to the 6th plus 3x plus 1, well, the degree is 6. And so if the degree is 6, I can have up to 5 turning points. Yeah, so using the second property, degree minus 1 will get me my maximum turning points. Now, a key word there, and I don't want to get a little bit too confusing because, again, this is more of a cute property versus something that we're going to see time and time again. But keywords here are minimum and maximum. So even though this property tells me that I could have up to 5 turning points, that is not a guarantee. In fact, this is what the graph looks like. I think roughly I may have changed the coefficient slightly, but this is what the graph looks like. And so if I'm looking at this graph, starting from the left to right, I kind of draw up and then I take a small dip. So there's 1 turning point, then another dip upwards, and that continues up to about, I don't know, 0.25. Take a dip down, I take a dip up. So 1, 2, 3, 4. This has 4 turning points. That is not breaking my definition. It's just saying that if I have this graph, there is no way I might have like 20 turning points or something weird like that. So it's kind of a helpful way to maybe check your work or maybe think about the general shape of your graph, but it is very limiting because it doesn't guarantee that's going to be the number. You're not guaranteed to have degree minus 1 turning points. You're not guaranteed to have the number of turning points plus 1 is equal to your minimum degree. But I think I'm going to probably let you guys have a note card on the midterm. I might take a little bit of space on that note card just to write these down so that if a question shows up and it says, here's your degree, what can we say about the number of turning points? All you would have to do is say, okay, well, the number of turning points is the maximum number of turning points is degree minus 1. And again, I think it shows up on WebWorks, so maybe worth jotting down on your notes or whatever real quick, and then once you see it pop up on WebWorks, you'll be prepped for it. Oh, nice. All right. Yep. Yeah. Okay. Yeah. The actual degree is 6 instead of 7, but exactly what I was kind of saying. The word minimum and maximum is valuable. Okay, that's the end of this section.